In this lecture, we are going to solve this problem called rotten oranges. So we will be given an m cross n matrix, and there will be three different type of elements in this matrix: rotten oranges, fresh oranges, or blank spaces. The rotten oranges, they will be represented by number 2. The fresh oranges, they are represented by number 1, and the empty spaces, they will be 0. So these cells will be given in the form of a 2D list or a 2D array, or you can say matrix. So what is happening is that every second a rotten orange is turning its neighbor fresh oranges into rotten oranges. Okay, so its neighbor are the oranges which are horizontally or vertically directly next to each other. The diagonal next elements, they are not considered as neighbors. Only the vertical and the horizontal neighbors, they will be considered as neighbor. Okay, so every minute more and more oranges are getting rotten, uh, and we have to find that if we are able to turn all the fresh oranges into rotten oranges or not. If that is not possible, then we have to return -1. And if it is possible to turn all the fresh oranges into rotten oranges, then we have to simply provide a number that tells after how many seconds we are able to do that. Okay, so this is basically, you can say, every second or every minute, uh, this is turning the next neighbors into rotten oranges. So for example, initially it is like this. So in the next second, this is the situation at time t equals to 0. At time t equals to 1, it turned its neighbor into rotten oranges. Okay, now these neighbors, they will turn their neighbors into rotten oranges, right? So at time t equals to 2, we can see that these two oranges, they will also be turned into rotten orange, since this orange is direct next to this one and this one, and this orange is direct next to this one. So at time t equals to 0, this also and this also, the both of these, that turn into rotten orange. In the next minute, at time t equals to 3, this fresh orange will be turned into rotten orange. Similarly, at time t equals to 4, this orange will be turned into rotten orange. So finally, all the fresh oranges, they are turned into rotten oranges, and it happened at time t equals to 4. In this example, we can see this is another example where we can see that there are no fresh oranges. Okay, so initially all the oranges, they are rotten, so we can simply return time t equals to 0 when there are no fresh oranges in the beginning. In this example, there is one fresh orange, but since this orange does not have any rotten orange directly next to each other, vertically or horizontally, that is why it cannot be turned into a rotten orange. Okay, this is rotten orange, but this rotten orange does not have this is neighbor, because it is not directly next to each other vertically or horizontally. Okay, so we return -1. In our example previously, in this one particular example, we had a single rotten orange, but there can be more than one rotten oranges in the beginning, like in this example. Okay, so what we have to do now, we have to turn the fresh oranges which are next to these rotten oranges into rotten orange simultaneously. Okay, so we have to keep doing this from both of these oranges at the same time. So what we are going to do, how we are going to solve this problem? For this problem, we are going to take a queue data structure, because we will be doing BFS. We will be doing BFS traversal, and the source point from where we will start the BFS are these rotten orange coordinates. So we will traverse through this matrix initially in the beginning, and then we will check what the total count of fresh oranges it is, because that is going to be used later on. We can directly tell if the total number of fresh oranges is 0, then we can simply return time t equals to 0 is the answer, because at time t equals to 0, there are no fresh oranges. So that is our answer. And one more thing that we also keep track of when we are traversing this matrix, as we are going to uh, insert the coordinate of these rotten oranges into our queue, and that is going to help us perform DFS. The beginning point for our DFS is BFS is going to be these different points. Okay, where we have rotten oranges. So now what we are doing, we are doing BFS at multiple sources at the same time. So this is a multi-source BFS algorithm, and it is there is nothing special about it. I'll show the code and tell you what are the changes that we will be making. And also this is what we call as the level order traversal, because in BFS we are traversing layer by layer. Okay, so firstly we traverse all the nodes which are at a distance of 1 from a node. Then we traverse in the next turn we traverse all the nodes which are at a distance of 2 from the source node. Okay, so that is how the BFS works. And since at a time we will be uh, covering a particular layer, for example will be covering the layer which is at a distance of 1 initially, then we will be covering the elements which are at the distance 2 from our element, okay, in the second turn. And similarly in the third turn we will be covering all the elements which are at a distance of 3 for our source element. Okay, so the level order traversal using the BFS can help us in determining how much time it takes to turn all the oranges into a rotten orange. Okay, so we will be what we will be doing is we will be starting our BFS from these rotten oranges, and then we will keep turning the fresh oranges into a rotten orange. And then once they are turned into rotten orange, we are going to insert them into queue, because now it is also a rotten orange, and we have to turn its neighbor into rotten as well, which are fresh. So that means BFS will continue from the next neighbor. So that is why we will also push them into the queue. Generally what we have to do is we have to keep a visited set so that we do not revisit a cell, okay, once it is visited. But that is not really required in this problem. Why? Because the fresh oranges are turning into rotten orange, and once it is rotten, we are not going to revisit them. We are only picking those oranges which are fresh, marking them as rotten, and then inserting them into the queue. Okay, so if the orange is turned into a rotten orange and is not fresh anymore, that means this will not be inserted into to the queue next time. Okay, so we do not need the visited set for that reason. Initially, this is our queue. We have 0, 0, 2, 1 inside our queue, which are the coordinates of the rotten oranges. We have these two different coordinates because we are going to start BFS from these two different positions. And in level order traversal, what we do is basically we calculate the size of the queue. All the elements which are there in the queue at a particular period represents the element which are at a particular distance from the source point. So what I mean by that is initially this queue has all the elements which are at a distance of 0 from our source point. For example, 0 comma 0, one of the source point is 0 comma 0, so the distance of 0 comma 0 from 0 comma 0 is 0, and the distance of 2 comma 1 from position 2 comma 1 is 0, right? So this represent all the different nodes which are at a distance of 0 from our source nodes. Okay, this is more than one BFS going on at a particular time, so that is why it is like this. If I was doing BFS from a single position, then this queue had only single element only. Okay, and so also we have calculated the total number of fresh oranges, which are 5. There are a total of 5 5 oranges which are fresh. Okay, so we have all the nodes which are at a distance of 0 from the queue. What we are going to do is we are going to take all of them out and we are going to insert their neighbor in this queue. Okay, so we will take all the elements out of this queue which are at a distance of 0 from the source node, and then we are going to insert all the elements in the queue which are at a distance of 1 from our source node. So what are the different nodes which are at a distance of 1 from our source node? This is at a distance of 1 because it is a distance of 1 from this source node, and this is also at a distance of 1 because it is a distance of 1 from this source node. This one particular orange, it is also at a distance of 1 from our source node, and this one particular orange is also at a distance of 1 from our this source node. So we can see that there are total of 4 different oranges which are at a distance of 1 from our source node. So the queue should remove these two elements, and when we are doing the next turn, when we are exploring the next layer nodes, then these two should be removed and these four should be there in our queue. Okay, and at time t equals to 0, we started from these two position, and what happened? Now the queue has four nodes, because those two, we have calculated all the neighbors for those two source nodes. We for those two nodes in the queue, we calculated their neighbors and inserted them into the queue. Okay, so the fresh oranges are 5 minus 4, because these four, so sorry, this one, this one, and this one, they were fresh earlier, right? So we turned them into a rotten orange because they are surrounded by rotten oranges. And the total number of fresh oranges now is 5 minus 4, that means 1. Okay, now we have four different nodes, right? These are four different nodes, and we have to now calculate the neighbor of these four different nodes, which means all the nodes which are at a distance of 2 from our source node. Okay, because these are this queue elements, they are at a distance of 1 from our source node. Okay, this was the source node, and the element are which are at a distance of 1 are there in the queue now. So we are going to calculate the neighbor for all of these four nodes, and we are going to then remove these four nodes, and then we are going to insert all the nodes which are their neighbor, and they are going to be at a distance of 2 from our source node. Okay, because since it is at distance 1, and then their neighbor which are also at a distance of 1 from this is going to be at a distance of 1 plus 1, meaning 2 from our beginning or the source node. Okay, so if I calculate the neighbor, then I can see that after this stage there is only a single orange, that is the neighbor for these four different particular nodes. There is a single fresh orange only. So after this stage, the queue should be emptied, because we have calculated the neighbor of all these four at once, and then we have removed them from the queue and inserted the one which is the neighbor at a distance of 2 from our source node. So now the fresh oranges are going to be 1 minus 1. Since earlier initially it was 5, then we found 4 rotten oranges, so it turned into 1. Now we turned one more fresh orange into a rotten orange, so it is 1 minus 1, meaning 0. Okay, so finally, since there are 0 fresh oranges, and even though there is an element in the queue, we don't care, because we have turned all the fresh oranges into rotten orange. Okay, so we will just stop our BFS algorithm. So at time t equals to 2, we were able to found our solution. Okay, so now this was all about it. Let's move to the Leetcode solution for this problem. Okay, so what I'm going to do is basically we will be firstly, we know we will be doing BFS algorithm, right? And in this method, what we are going to do first, let's calculate the rows and columns, which are the length of the grid and the length of the first item from the grid, which is basically the length of the row, is equal to the number of columns. Okay, I'll increase the font size, and this much is fine. Okay, so for I in range rows and for j in range columns, we are traversing through the matrix, and we are going to check if the current cell is having value of 1, that means it's a fresh orange, right? So we are going to increase the number of fresh oranges. Okay, and we have to first declare the variable for fresh oranges. So fresh oranges plus equals to, sorry, equals to 0. Initially the fresh oranges are 0, then we are increasing their number whenever we encounter a fresh orange from the grid. If this item is actually having value 2, then what does that mean? That means it's a rotten orange. So what we will be doing, we will take a queue data structure, and this will be coming from collections.dq in Python. Okay, so this is just a queue data structure, and within this queue we are going to add our rotten orange. So we will represent our rotten oranges using their coordinates. Okay, so I comma j is basically the coordinate of this rotten orange. Now we can check if the count of the fresh oranges is 0. That means initially all the oranges are rotten. Okay, there are no fresh oranges. So if there are any oranges, then they are rotten. So if fresh oranges equals to 0, then we have to just return 0 because it is there are no fresh oranges in the beginning. Now what we can do is we have to check while there are fresh oranges. Okay, so while there are fresh oranges and while there are elements in the queue, if any of these condition is false, then we will come out of the while loop. Okay, so what we are going to do is basically we are going to check the neighbor. We are going to calculate the neighbor for all the elements in the queue, since we have to get all the elements at a particular distance, at a particular layer in our BFS algorithm. So how can we check for the neighbor of all the elements in our queue at the same time? We have to run a for loop for that. For I in range length of queue, what we will be doing is we will be taking the element out from the queue. So queue dot pop left is going to give us the element, right? And we are going to take x and y coordinate out of it, since the elements in the queue, they represent the coordinate. So let's take x and y out from it. And then what we are going to do for this particular rotten orange that has a coordinate x and y, we are going to turn its neighbor fresh oranges into rotten oranges. Okay, so there can be 4 different directions, okay, in which we can go. So what we can do is we can declare another method. Let's just call it is safe. So is safe is the name of our method. Okay, it will take the node that will have the, instead of node, let's call it position because it is having x and y value. So it is going, and the next thing that we are going to pass is the grid. Okay, so if let's take x and y out from the position. Okay, so if x is less than 0 or x is greater than equals to the length of grid, or y is less than 0 or y is greater than equals to length of grid 0, if these conditions are satisfied, that means our position is outside the board, outside the grid, then we have to return false because it is not safe. Otherwise, if this particular element at the new position is not having value of 1, that means if it is not a fresh orange, then also we don't care because we have to turn fresh oranges only into rotten orange. Okay, so now we can use this method is safe, which will have position and the grid. So if is safe in the position, we can pass x plus 1 comma y. Okay, and then we can pass the grid. If this is, we can go to this position, that means there is a safe orange at the position of x plus 1 comma y, and this just represents the downward direction. So what we are going to do, we are going to just decrement the count for the fresh orange. Okay, because we have turned this fresh orange into a rotten orange. Okay, so we are decrement the count, and now since we are turning this fresh orange into a rotten orange, what we are going to do, we are also going to insert this into our queue. Okay, so within the queue we will add this x plus 1 comma y. Now we are going to do this thing 3 more times because there are a total of 4 different directions. Okay, and see, so let's just copy this command once, this code once more. And okay, so we have 4 different directions, right, for x plus 1 comma y, and there is going to be x minus 1 comma y. So this is x minus 1 comma y, and then there are going to be x comma y plus 1. and there is going to be x comma y minus 1. Okay. Now, after this, we know that we have calculated and inserted all the neighbor for the elements which are there in the queue, inside the queue. Okay. So, since we are running this for loop for the length of a queue, so all the elements which are already there in our queue, we are taking them out one by one. And then what we are going to do for each of those elements, we are calculating their neighbor in four different directions, and then we are again inserting them inside our queue. So after this step, the queue will be emptied from the elements which were already there inside it. So queue will be empty, and then all the elements which are the neighbor of the existing queue elements are going to be inside the queue. Okay, so all the elements which are from the forward layer in our BFS algorithm, in our BFX algorithm, all the elements which are in the next layer are going to be inside the queue. Since in BFS, we explore nodes layer by layer. All the nodes which are at a distance of 1, then all the nodes which are at a distance of 2, all the nodes which are at a distance of 3. We do it like that. Okay. So now, one thing that again we have to do is, firstly, we have to also calculate the time. So we will take another variable, let's call it timing. And each time we are done with this for loop, we will increase our timing. Okay, because at a time we are calculating the neighbor for all the nodes in the queue and then going to the next layer. And the next layer will have all of these appended elements from the current existing queue element neighbor. Okay. So in the end, what we can do is basically we can check, we can say that you can return the timing variable if the fresh oranges have count of 0. So if the fresh oranges are 0, otherwise we will return -1. Okay. So that is it. In the end, we are making sure that the total number of fresh oranges now are 0, because each time we are turning a fresh orange into a rotten orange, we are doing this by decreasing the total number of fresh oranges and then inserting that particular orange which we turned into rotten orange inside of our queue. So let me just submit our solution. Okay, so there is one on. So we did not actually define this BFS method. We just did it all inside of our this one. So BFS algorithm is just this. So declaring a queue, and then you are and then while there are elements in the queue, you are taking element one by one from the queue and looking for the neighbor of that particular node and then inserting them inside of a queue. Let me check if I am making any more mistakes in this code. So one thing in this is safe method is we forgot to return true in the end if the orange is also a fresh orange and it is inside the grid, then we can take it. Okay, so we have to return true in the end. And apart from that is here I didn't q dot add, but this is actually q dot append. And in the last here I also did some typo. This is x comma y minus 1, not x comma y minus 1. And one really important thing that we have to do is, before inserting a orange, we have to first mark it as rotten. We cannot append orange into a cube before we mark it as rotten. Okay, so how we are going to do that? We are going to set the coordinate for that particular orange as, so we are going to set the value for that particular orange equals to 2. Okay, grid -1, y equals to 2. Here also we have to do grid x y plus 1 plus 2. I minus 1 equals to 2. Okay, in the end, we are just returning the time that it took. If the fresh oranges are equals to 0, if there are fresh oranges not equals to 0, meaning if there is still a fresh orange left, we will just return minus 1. Okay, let me now run the code. Is safe is not defined. Okay, so is safe method is actually defined over here, but we forgot to prefix this with self keyword. Okay, now our submission it is running. Let's just submit our code. Okay, so our code it is working. Let me re-explain this solution. So we have this is safe method because before we are turning an orange into a rotten orange, we have to first check that it is a fresh orange. Okay, and also we have to check that the coordinates for that orange they are within the cell, they are within the grid. Okay, so we can do that by checking these conditions. And within our rotten orange, so we what we are doing is initially we are traversing through the whole grid, and within the grid we are checking if the current grid cell it is representing value 1, that means it's a fresh orange, so we are incrementing the count of fresh oranges. If it is having value 2, then we know that it is a rotten orange, so we are adding it to our queue. Okay, so in the BFS, when we take a queue, initially we append the source node in the queue from where we start doing our DFS algorithm. In this solution, what we are doing is that we are inserting we may insert more than one item in the queue initially. Why? Because there are more than one source node for our BFS algorithm. We will be doing simultaneous BSF from different source node, okay, at the same time. Now we have our while loop. So this while fresh oranges are greater than 0 condition will break our BFS algorithm. We will break out of this BFS algorithm before it is completed if we have no more fresh oranges. Okay, and in our BFS algorithm, what we are doing, we are getting all the elements which are there in the queue already. So initially in the queue, there are going to be only source nodes only, and source nodes we know are at a distance of 0 from the source node itself. Okay, any element from itself is at a distance of a 0. Now what we are doing, we are taking all the elements in the queue, then calculating the neighbor for these nodes which are there already in the queue. Then we take all of them outside the queue, and then we are within the queue which is empty. After taking all of them out, we are inserting now these new nodes which are the neighbor of the nodes that were earlier in our queue. Okay, so basically these are the different nodes from the these are nodes from the next layer, or which are at a distance of +1 from the existing nodes in the queue. Since they are at a neighbor are always at a distance of 1 from the their neighbor cells or nodes. So there are 4 different directions. So in our BFS algorithm, we are checking within these 4 direction. Okay, so if it is safe, meaning it is a fresh orange, and it is the place for the orange is within the grid, then what we are doing, we are decrementing the count of the fresh oranges. We are marking the orange as a rotten, and then we are appending it inside our queue. And we are doing this for all the 4 different directions, for x plus 1 comma y, for x minus 1 comma y, x comma y plus 1, and x comma y minus 1. And when we are done doing this for calculating all the 4 direction neighbor in all the 4 direction from our cell from our queue items, for all the items in the queue, once we are done with it, sorry, here in the for loop, once we are done with calculating the neighbor for all the nodes which are there in the queue, we will increment the timing. We are incrementing the timing because this time we are going to the next layer. Okay, so In the end, finally, when there will be zero fresh oranges, or the BFS algorithm will stop because there will be no more element within a queue. Okay. Then what we will do, we will check if there are fresh oranges equals to zero. If they are zero, then we will return the timing. Otherwise, we will just return -1. So this was the solution for the problem rotten oranges.